Ptolemy's Almagest, the greatest work of astronomy from the ancient world. Ptolemy, the great Greek astronomer, produced the most impressive model of the solar system from the ancient world. His model accounted for all observed motions of the stars and the planets, including the daily rotation of stars, the yearly rotation of stars, the speeding up and slowing down of the sun and the planets, and also the strange periodic backward motion of the planets, known as retrograde motion. As a result, Ptolemy could predict the location of celestial bodies with astonishing accuracy, even over very large time spans. In this lecture, we'll take a close look at his phenomenal book on the matter, which was later called the Almagest by the Arabs, meaning the greatest. It is one of the most important books in the history of the world. Now, let's start. Hey, good to see you. This is Stephan, author of In Search of the Sublime. On this World History channel, we'll trace humanity's relentless pursuit of scientific truth, moral excellence, and enlightenment. We'll meet anyone from Mesopotamian astronomers and Indian yogis to Greek philosophers and Enlightenment scientists. And you'll meet them firsthand using primary sources, giving you valuable insights that transcend the surface-level understanding you get on other channels. Go check it out for yourself. Let's start. Ptolemy, who lived in the 2nd century AD, is the most influential ancient astronomer. He was born in Alexandria in Egypt, which at the time was part of the Roman Empire, while he himself was of Greek descent. His model of the solar system was remarkably accurate at predicting the complex motions of the planets. And in fact, it remained the dominant model for 1200 years, until it was finally replaced by the heliocentric model of Nicholas Copernicus, who was born in the 15th century. Ptolemy's work, the Almagest, is a massive work. It is filled with extensive astronomical tables about the positions of the sun and the planets, and also endless complicated geometric figures, as you can see here. Let's start with Ptolemy's fascinating introduction to the Almagest, in which he praises mathematics as the ultimate tool of science. Ptolemy dedicated his Almagest to an unknown figure named Cyrus, who is mentioned in the first sentence of the text. He starts by telling Cyrus about the different types of knowledge that exist. The first line reads, "Those generally engaged in philosophy, Cyrus, seem to me quite rightly to have distinguished the theoretical from the practical part of philosophy." Practical knowledge, according to Ptolemy, is about making or doing things, while theoretical knowledge he defines as knowledge obtained for its own sake, a quintessential Greek phenomenon. Ptolemy then followed the great philosopher Aristotle in dividing up theoretical knowledge in theological, mathematical, and natural knowledge. Theological knowledge, he writes, is uncertain because it cannot be verified by the senses. Natural knowledge, which is about things on this earth, he also considered uncertain, which sounds strange today, but which was a common Greek thought. According to the Greeks, the materials on earth are by their nature perishable and ever-changing, and as a result, the Greeks believed that the physics of the earth was fundamentally different from the physics of the heavenly bodies. The motions of the moon, the sun, and the planets and the stars seemed unchanging, or always such in the words of Ptolemy. So natural knowledge was also uncertain. And then finally there was mathematical knowledge, which is based, quote, on forms and motions, figure, quantity, size, place, and time, which are today objects of physics and mathematics. And according to Ptolemy, only this gives us true scientific knowledge. In his own words, he wrote, "One might call the other two kinds of theoretical philosophy conjecture rather than scientific knowledge. The theological, because it is utterly beyond the senses and unobtainable, and the natural, because of what is unstable and obscure in matter. For this reason, those who pursue philosophy would never hope to come to agreement about them. But the mathematical kind alone, would provide certain and steadfast knowledge to those who practice it, as its mode of proof arises through indisputable paths, arithmetic and geometry. Ptolemy then added that the mathematical approach is also the best way to study theological questions. Quote, "For it alone is capable of making sound conjectures about the unmoved." And the unmoved here is Aristotle's word for his rational God. I have an entire other lecture about this. And Ptolemy continues, the mathematical approach is also the best way to study natural knowledge, since objects on Earth can also be described in terms of motion, be it motion that is ever-changing. Then Ptolemy ends his introduction with a thought that is also quintessentially Greek, namely that the mathematical order in the universe is both beautiful and divine, and therefore make the mathematical sciences a spiritual pursuit. We read, "With regard to virtuous conduct and character, this science, above all things, could make men see clearly. The constancy, order, symmetry and calm which are associated with the divine make its followers lovers of this divine beauty, and it changes their own natures to a similar spiritual state. That is, learning the mathematical order of the universe makes us divine." Now, let's build up Ptolemy's model of the solar system step by step. First of all, following Aristotle, Ptolemy recognized that the Earth was a sphere. He writes, "The Earth is spherical, for it is not possible for all observers on Earth to see the sun, moon and the rest of the stars rising and setting at the same time." We continue, "Rather, those living in the East invariably see them rise and set earlier than those in the West. And the drawing that I made can help you understand this. You see here two figures on a different part of the globe. And as you can see, the figure on the right can see a lot of stars that the figure on the top cannot. And this is of course because of the curvature of the Earth." He continues, "The farther north we travel, the greater number of southerly stars are hidden, and the greater number of northerly stars are revealed." Ptolemy then also gives the following argument. We read, "If we sail towards mountains, their magnitude are observed to increase gradually, just as if they were rising out of and had previously sunk into the sea itself due to the convexity of the surface of the Earth." And here we can see a modern version of this experiment. If you sail towards Toronto, it appears as though the skyline is slowly rising out of the sea. And this is because all those tall skyscrapers are hidden behind the curvature of the Earth. The simple drawing from the 16th century helps us understand this. A person looking from that castle window can see the tip of the ship, but not its bottom, because the bottom is hidden behind the curvature of the Earth. Now we'll focus on the motions of the stars. The stars make various circular motions at the same time. Let's start with the simplest. If you would follow the stars during the night, you'll quickly discover that they rotate around us every 24 hours. Just as you can see in the image, all stars seem to move around an axis, and this axis points to the polar star. You can easily see this if you take a picture with a camera with a very long exposure time, which you can see here. You clearly see that all the stars seem to move around a single point. And very close to that point, although not exactly in it, you see a tiny star. It isn't even a very bright star, and that star is now called the polar star, because it happens to be at the extension of the axis of the Earth. Using this figure, we can also understand that some stars rise and set every day, while other stars remain, as Ptolemy called it, ever visible. And this motion of the stars is dependent on your latitude. Imagine, for instance, that you're standing on the North Pole in this image. In that case, you can see all the stars circling above you, and none of the stars are rising or setting. While if you were to stand on the equator, you can see all stars rising and setting above you, as you can see in this photograph. Interestingly, all stars seem to move in unison around the Earth, leaving the distances between the stars constant. Anaximenes from the 6th century BC explained this by assuming that all the stars are stuck on a crystalline sphere, and that it was the sphere that was moving, not the individual stars. For how else could all the stars keep their distances fixed? While today, of course, we know that this motion is instead caused by the rotation of the Earth around its own axis, while the stars stay in place. Secondly, the stars also make an annual rotation in the direction of the zodiac, and this takes 365.24 days. And the zodiac, as you can see in the image, is inclined at an angle of 23.5 degrees. And all the stars move in that direction around the Earth every year. Today we know that the zodiac is in fact the plane of our solar system, as you can see here. And the angle of the zodiac is caused by a tilt in the Earth axis. Now, why does the motion of the Earth around the Sun cause the yearly rotation of stars, you might ask? Well, as the Sun revolves around the Earth, the night side of the Earth points in different directions. If this is the Sun and this is the Earth, now the night side is on this side. And in that case you can see the constellations that are located here. While half a year later, this is the night side of the Earth. And now you can see the constellations over there. And in this way the entire zodiac rotates around us every year. Thirdly, there also is a very slow motion of the stars, which is known as precession. And we now know that this is caused by a periodic spinning of the axis of the Earth, which takes about 26,000 years. Hipparchus in the 2nd century BC was the first to have discovered this effect, and he did so by comparing his own measurements with the measurements of its predecessors, finding that all the stars had shifted somewhat. Now we turn to the motions of the Sun, the Moon and the planets. The Sun, the Moon and the planets all move along the zodiac, which, as we've discussed before, is that plane of our solar system. You can see this beautifully in the following image. Here you see 3 planets, possibly Mercury, Venus and Mars. And as you can see, they can be found on the same line. And if you now extend that line below the horizon, you'll also find that the Sun is on the same line. And so is the Moon. Now, let's first focus in on the Sun. The Sun appears to orbit the Earth every 24 hours. And this we now know is because of the rotation of the Earth around its own axis. On top of this, the orbit of the Sun also shifts up and down during the year. In June, during the summer solstice on the northern hemisphere, the Sun reaches its highest orbit above the horizon, resulting in the longest day of the year. While in December, during the winter solstice, the Sun reaches its lowest orbit above the horizon, resulting in the shortest day of the year. And when the orbit is right in between, we speak of an equinox, where night and day are of equal length, and there's one during spring and one during autumn. During the equinoxes, the Sun rises exactly in the east and sets in the west, with exactly half the orbit of the Sun now above the horizon, causing that equality between day and night. Both the solstices and the equinoxes can also be explained by the tilt of the Earth. During the summer solstice, the northern hemisphere is tilted towards the Sun, making the Sun appear higher above the horizon. And during the winter solstice, half a year later, the northern hemisphere is tilted away from the Sun, making the Sun appear lower above the horizon. We'll now discuss how Ptolemy positioned the Earth in his model. The Earth, Ptolemy claimed, was at the center of that sphere of the fixed stars, which he claimed was evident since we always see half of the zodiac, which he claimed could only be true if we were exactly in the center. For think about it, if we were off-center, you'll see a smaller part of the zodiac during half the year and a bigger one during the rest. Also, Ptolemy reasoned, the Earth has to be in the center of the daily orbit of the Sun, since otherwise day and night would not be of equal length during the equinoxes, that is, when the sun rises exactly in the east and sets in the west. And since the Earth is always at the center, according to Ptolemy, it must also be at rest. He wrote, "Assume that, for argument's sake, the heavens are unmoved, while the Earth revolves around its own axis from west to east. Such a thing would seem quite ridiculous based on what occurs around us and in the air. For the revolution of the Earth is the most violent of all motions, causing everything not standing on the Earth to appear always to be making a single motion opposite to the Earth." So basically, if the Earth was spinning around its own axis and I would throw up a ball, the motion of that ball would be deflected because of the motion of the Earth. Quite a sensible idea, but Galileo would later prove that this was not the case. To refine his model further, Ptolemy had to include the observation that the Sun and the planets speed up and slow down along their paths, which is now known as anomalistic movement. Let's start with the Sun. Hipparchus in the 2nd century BC had already measured that the seasons were of slightly different length. It takes 94.5 days from the spring equinox to the summer solstice, and 92.5 days from the summer solstice to the autumn equinox. From this, he estimated that the Earth was not in the center of the yearly orbit of the Sun, but instead he calculated it must be 1/24th of the solar radius off-center. Although, as said before, the Earth is in the middle of the daily orbit of the Sun, just not in the yearly orbit of the Sun. It's all quite complex, but that's what it is. The planets are even more complicated, as they also exhibit retrograde motion, meaning that the planets sometimes halt in the forward motion, move back a little, and then continue their motion forward again, as you can see in this combined series of photographs of the planet Mars. And here we see an 18th century image of the complex motions of Venus and Mars. It is horrifically difficult to describe. In the 4th century BC, Plato suspected that there must be a way to simplify this messy motion of the planets. And as a result, he challenged the intellectuals of his day to attempt to explain these motions in terms of simple circular motion with constant velocity. And various Greek astronomers took up this challenge. In the 3rd century BC, Apollonius managed to describe this retrograde motion with so-called epicycles. An epicycle, as you can see in this image, is a small orbit whose center moves in a larger orbit. So they are circular motions within circular motions. So in this way, the motions of the planets were indeed reduced to circular motion, just as Plato had suspected. But there was one problem left. Plato also predicted that the velocity of the Sun and the planets should be constant, but this wasn't the case in Apollonius' model. To resolve this, Ptolemy added the so-called equant, which is depicted in this image. And from this point, called the equant, the motion of the Sun indeed appears to be constant. Say, for example, that it takes the Sun the same amount to move between point A and point B, and also between point C and point D. As seen from the Earth, the Sun has moved by a much larger angle between C and D, and as a result the velocity of the Sun appears higher here. But if we study the same motions of the Sun, but now from the equant, the Sun has moved by exactly the same angle from A to B and from C to D, as you can see here. And this makes it appear that the Sun moves with a constant velocity from this point. And Ptolemy then showed that observing the motion of the Sun from the equant approximated the observed motion of the Sun extraordinarily well, which was a huge success. Today, by the way, the speeding up and the slowing down of the Sun in its yearly orbit is explained by the fact that the planets, which includes the Earth, make a slight elliptical orbit around the Sun and not a circular orbit. The closer we get to the Sun, the quicker we move because of the gravitational attraction of the Sun. But the addition of the equant matches this movement reasonably well, making Ptolemy's system very accurate for its time. Some details which Ptolemy already mentioned in the Almagest already hint at the heliocentric model of the solar system. Let's take a look. Ptolemy, for instance, tells us that Mercury and Venus, the inner planets, always stay very close to the Sun. Mercury always within 28 degrees and Venus always within 47 degrees. Ptolemy mentions this but gives us no explanation. Why are they always close to the Sun? Well, we now know that this is because they orbit the Sun, and these are the two planets closest to the Sun, so they must always stay in the neighborhood of the Sun. Ptolemy also noted that the motion of the center of the epicycles of the inner planets also equal the motion of the Sun as they orbit the Earth. And in fact, we now know that the Sun is in fact in the center of these epicycles, as you can see in this image. But Ptolemy didn't know that, because he didn't have accurate distances to the Sun and the planets. Ptolemy still believed that the Sun was on its own orbit, and that the other planets made epicycle motions above and below it. But in reality, the Sun is at the center of the epicycle. Why? Because the planets revolve around the Sun, as you can see in this image. In the image, you can directly see that the inner planet is revolving around the Sun. And what about the outer planets? Well, that's a bit more difficult to spot, as those outer planets are so far away from the Sun. But Ptolemy already knew and wrote down that the radius of the epicycles of the outer planets always run parallel to the radius of the Sun. So if the Sun rotates around the Earth, the outer planets rotate in their epicycle. And the epicycles of the outer planets all have periods of 1 year. And Ptolemy wrote all this down without searching for an explanation. This seems too much of a coincidence. And by the way, Ptolemy did not know that the epicycles of the outer planets are also the same size as the orbit of the Sun around the Earth. So that's even another similarity. So the motion of the outer planets perfectly mimics the motion of the Sun around the Earth. So how can we explain this? Well, if you view this motion from the Sun, that epicycle motion perfectly disappears, for they're both moving in the same way. So as seen from the Sun, there is no epicycle movement. As seen from the Sun, the planet only makes a circular motion. And this too is evidence for the heliocentric model. As said before, Ptolemy already knew about all of these curious coincidences. And he mentions them explicitly, but he saw no need to explain them, even though they contained the seeds for the later heliocentric model. So, in order to better understand that strange backward motion of the planets, that retrograde motion, I made this JavaScript model. And I did this the easy way. I started with this left side, with the heliocentric model, which is of course quite easy to program. I simply added the correct distances and the correct velocities of the planets. And then I used a simple mathematical trick known as a coordinate transformation to go from this model to the geocentric model. And to do this, I simply calculate the distance of the Sun and the planets as seen from the Earth at every step. And then I simply plot those distances with now the Earth here at the center. And remarkably, this only takes a few lines of code, and then you can get this incredibly complicated system. Now let's start with the inner planets. Let's start first with Mercury. As mentioned in the lecture, you can easily see that Mercury rotates around the Sun, even when you look at the geocentric picture. And here we clearly see that that backward motion that you see here, for instance, is caused because Mercury is rotating around the Sun while the Sun rotates around us. The same goes for Venus. Let's add Venus now. So here we see both Mercury and Venus, and as you can see, they're both circling around the Sun, as is consistent with the heliocentric model. The only difference being that Venus takes quite a larger orbit. And the pattern of Venus, by the way, is especially beautiful, since it creates a 5-pointed flower, as you can see right here. You see those 5 petals right there. Not a bad idea for a tattoo, by the way, this image. Let's now look at the outer planets. Here we have Jupiter and Saturn, and I speed it up a bit. So, what do we see here? If you look carefully, you see that the retrograde motion of the outer planets beautifully mimics the rotation of the Sun. The Sun and the outer planets seem to move in unison with each other. And this is of course because we have to view this motion actually from the Sun instead of from the Earth. As seen from the Sun, the outer planets make a simple circular orbit, as you can see here. And this is also evidence for that heliocentric motion. It would have been too crazy a coincidence if the outer planets moved exactly in sync with the Sun all the time. Finally, we'll discuss Ptolemy's work called the Planetary Hypothesis, where he attempted to measure the size of the universe. To do this, he used the assumption that the spheres of the planets were stacked directly on top of each other. For in this way, he reasoned, there was no vacuum between those spheres. And Aristotle had claimed that a vacuum cannot exist in nature, even though of course we now know this to be untrue. But using this assumption, he found the mean distances for the planets. We read, the distances of the planets may be determined without difficulty from nesting those spheres on top of each other. He then equated the distance to the sphere of the fixed stars with the radius of the cosmos itself. And although his results were way off, it was an ambitious attempt nonetheless. And there we have it, Ptolemy's groundbreaking model of the solar system. I hope you were inspired by this lecture, and if you want to know more about Greek astronomy or any other topic from world history, then read my book In Search of the Sublime. You can read it completely for free on worldhistorybook.com, or you can buy a physical copy on Amazon. See you next time. Bye bye.